In the last video, we talked about building and using the MO diagram for HF. In this video, we're going to build an MO diagram for CO, carbon monoxide. So as always, we need to start off by determining what the valence atomic orbitals and valence electrons of the atoms in our molecule are. So if we've got carbon monoxide, we have carbon with an electron configuration of 1s2, 2s2, 2p2, meaning its valence atomic orbitals are the 2s and the 2p, and it has 4 valence electrons. And oxygen has an electron configuration of 1s2, 2s2, 2p4. So its valence atomic orbitals are also the 2s and the 2p, and it has 6 valence electrons, which means we're going to have a total of 10 valence electrons when the time comes. Again, we've been given a diagram showing us the energies of these atomic orbitals. Again, the y-axis here is energy divided by the Rydberg constant, or energy in Rydbergs. We have, of course, 3 degenerate 2p orbitals for both carbon and for oxygen. The fact that only 2 of them in carbon bring any electrons, completely irrelevant. Doesn't matter. As soon as your valence shell is the n equals 2 shell, you bring the 2 s's and the 2 p's, the full set of 4. So, once again, we've been asked which atomic orbitals will combine to make molecular orbitals. So we're going to take our atomic orbitals and divide them out into sigma symmetric and pi symmetric categories, and then check those for compatible symmetry and compatible energies. So we have the sigma category and the pi category, and our 2s atomic orbitals look like spheres, and our 2p atomic orbitals, each atom has an up and down, a left and right, and a forward and backwards, and same for oxygen. The phases are completely arbitrary. All that matters is relative phase within a particular atomic orbital. So looking at those, the easiest category is always to say that the 2s atomic orbitals must be sigma symmetric. So in this case, we've got the 2s on the carbon and we've got the 2s on the oxygen. Looking at our 2p orbitals, the one that's pointing left and right is the one that is pointing directly along the bond axis. So 1 2p orbital on carbon and 1 2p orbital on oxygen is going to also be sigma symmetric. And then the other 2p orbitals each have plane, a nodal plane passing through the bond axis, so they are all pi symmetric. So we're going to have a 2p on the carbon and a 2p on the oxygen, and the other 2p on the carbon and the other 2p on the oxygen. So let's say, for the sake of argument, that these are the up and down ones and these are the forward and backwards ones. And that is all of our atomic orbitals assigned either sigma or pi symmetry. Now that I've done that, I label my p orbitals with x, y, and z. The sigma category only has one direction of p orbital, so that makes it the 2pz. The pi category has 2 directions of p orbital, and so one direction gets assigned to be x, doesn't matter which, but be consistent. It must be the same direction on both atoms. And the other gets assigned to be the 2py. Now 2px can't mix with 2py, they're pointing in different directions, so we'll subdivide our pi atomic orbitals right away into the ones pointing in one direction and the ones pointing in the other direction. Then we do a quick energy check to see if the 2px on carbon is actually close enough to the 2px on oxygen to mix. So there's our energy of the 2p on the carbon, and there's the energy of the 2p on the oxygen, and that gap right there in the middle, that sure looks smaller than 1 Rydberg, so I think we're good to mix those. Each group of pi symmetric atomic orbitals that are able to combine is therefore going to contain a 2p orbital from carbon and a 2p orbital from oxygen. When we look at the sigma symmetric atomic orbitals, we can see that the 2s atomic orbital on the oxygen is right on the border there. That is about 1 Rydberg, and I'd have to have actual numerical values to tell whether it was above or below. But that means we're right on that cutoff. So it's probably reasonable to combine them. And I'm going to go ahead and do that just so you can see what happens in cases where you have more than 2 atomic orbitals that you want to combine to make molecular orbitals. But you're right on the border. And we'll see in the computer-generated diagram that the computer says, yeah, we're really on the border. There's very little mixing. But anyway, either way, you get a very similar answer. And this is getting into the cases where if we wanted an absolute answer, we'd ask the computer and then we'd have to pick which of the 82 different ways we can do the calculation. And so the good news is in the region of reactivity, in the region where we're interested in looking at the MO diagram to talk about how carbon monoxide is going to react, it's going to wind up the same either way. Do your best, make smart judgment calls, and I'm going to understand that when the energy gap is exactly 1 Rydberg, we can kind of go either way on it. Anyway, that 2s is definitely within a Rydberg of the 2p on carbon, and it's definitely within a Rydberg of the 2p on oxygen, and the 2p on oxygen is definitely within a Rydberg of the 2p on carbon. So the 2p on carbon, the 2p on oxygen, and the 2s on carbon all definitely in the same group. The 2s on oxygen, we can go either way. So let's dump all those into one big group of 4. So which atomic orbitals will combine to make the molecular orbitals? We've got 3 sets now. A set of px's, a set of py's, and a set of sigma symmetric. So, anytime you have categories with different numbers of atomic orbitals in them, I always start with the category with the fewest atomic orbitals because they're always the easiest to do. So in this example, we're going to start by looking at the pi symmetric atomic orbitals of carbon monoxide and use them to generate the pi symmetric molecular orbitals of carbon monoxide. So if we take the 2px, I think I called this one, on carbon, and we mix it with the 2px on oxygen in phase, they're going to come together and we're going to get a pi bonding molecular orbital on our carbon monoxide. If we combine these atomic orbitals out of phase, then we're going to get a pi star or anti-bonding molecular orbital as well. So this is going to kind of point out this way a bit, and this is going to kind of point out that way a bit. So that was our 2px box taken care of. Now for our 2py box, we do the same thing, rotate it 90 degrees forward. We suffer through my artistry. I have a p orbital, and there's the other side of it, far away from me, and a p orbital, combining in phase to make a pi symmetric molecular bonding orbital, a pi MO. And then we do the same thing. We combine them out of phase. There's my C, there's my O. And we get a pi star or anti-bonding pi symmetric molecular orbital. Now, if I wanted to factor in the polarization, then I would have to look at which of these p orbitals is lower in energy than the other. 2po is lower in energy than 2p on carbon, therefore closer to pi. And similarly, the 2p in carbon is going to be higher in energy than the 2p on oxygen, and therefore it's going to be closer to the pi star. So the pi MO, if we factor in polarization, should look bigger on the oxygen than it does on the carbon. And this is where my artistic lack is really going to come into play, and you're going to be really happy to see those nice computer pictures in a few pages. And so this is me attempting to draw a pi orbital that is bigger on the oxygen because it's polarized toward the oxygen, because pi is closer in energy to the 2p on O than it is to the 2p on carbon. On the other hand, the anti-bonding, the pi star, is closer in energy to the carbon, so it's going to be bigger, polarized toward the carbon, and we might get a picture that kind of looks like this. And there's no way I'm drawing that in the other direction. Assume that you can take those pictures and spin them forward 90 degrees. So building the pi symmetric molecular orbitals, actually pretty straightforward, very similar to what we did with the homonuclear diatomics. Now we want to take our sigma symmetric atomic orbitals and combine them to make sigma symmetric molecular orbitals. So we are combining 2s on carbon, 2s on oxygen, 2pz on carbon, and 2pz on oxygen. And that is going to give us a total of 4 sigma symmetric molecular orbitals. So CO, 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 4 of them. In my opinion, the easiest way to do this is to predict the pictures of the lowest energy one, and then predict the picture for the highest energy one, and then use nodes to fill in the middle. And so when we're building these molecular orbitals, we can pick and choose which atomic orbitals we want to use or see show up in each of the molecular orbitals that we generate. So my lowest energy possible combination is going to take any set of those and combine them in such a way that we have the lowest energy combination, the most constructive interference, the fewest nodes. And the best way to combine those atomic orbitals and make something with as few nodes as possible is going to be to take the 2s on the carbon and combine it in phase with the 2s on the oxygen, and that's going to give you something that looks like a nice sigma bonding molecular orbital. That is the way to combine atomic orbitals from that set, generating a molecular orbital with the fewest possible nodes and maintaining the symmetry of the molecule. So you can't make anything weird and lopsided that has different symmetry than the overall molecule does. If I want to generate the molecular orbital with the most possible nodes from that combination of atomic orbitals, what I would do is I would take a 2p orbital on the carbon and a 2p orbital on the oxygen, and I would combine them out of phase, and that is as many nodes as I can possibly put in a molecular orbital generated from this set of atomic orbitals. And so it would look kind of like this. So here we have 0 nodes, and here we have 1, 2, 3 nodes. And that's going to be the highest energy molecular orbital from our set. And now we can fill in the middle by increasing the number of nodes every time we go up a step in energy. So if the lowest energy one has 0 nodes, then the next one up is going to have 1 node, and the next one up is going to have 2 nodes. And now I just have to think about how to do that. How can I make a molecular orbital with only 1 node from that set of atomic orbitals? Well, one way to do it would be to combine the 2s from the carbon with the 2s from the oxygen, but this time out of phase. And then it's going to look kind of like this, and there's my node down the middle. How do I combine atomic orbitals from that set and make something with 2 nodes? Well, I probably want a node down through the carbon and a node down through the oxygen, and so what I'm going to be looking at doing then is taking a p orbital on my carbon and a p orbital on my oxygen and combining them in phase to give me something that looks like this. And this one kind of looks anti-bonding, and the next one up kind of looks bonding. Now, the nodes don't have to be exactly where I placed them. There are other ways to generate molecular orbitals with those number of nodes, at least the 2 middle cases, by combining different sets of those atomic orbitals. For example, I could have made the 1 node version by combining the S on the carbon in phase with the P on the oxygen, and that would also have given me something with 1 node, and that would be a completely reasonable suggestion for you to have made because it is compatible with the symmetry of this molecule. So there are going to be different ways to get at the same overall answer, and you'll see when we get to our diagram that that's okay. Sometimes we make judgment calls, and we want you to think about what is and isn't reasonable. We don't want you memorizing pictures. So we have built a set of 1, 2, 3, 4 sigma symmetric molecular orbitals from our 4 sigma symmetric atomic orbitals. And it's also okay if not every single atomic orbital shows up in every single molecular orbital, as long as they all show up in at least some of them. Because the way in which they combine means you're not always going to be able to see each atomic orbital in every molecular orbital. So from there, I take my molecular orbitals that I've built and I do my best to guesstimate a reasonable set of energies. So I had my energy scale here, and I had my carbon, and I had my oxygen, and I know I had a relatively low energy 2s for oxygen down here, and then the 2p was more up here. And if I look at my original diagram, the 2s for carbon was below the 2p. The 2p for carbon was above the 2p for oxygen, and you'll notice that the energies for equally named atomic orbitals in different atoms, so for example, the 2p in carbon versus the 2p in oxygen versus the 2p in fluorine, they go down left to right across the periodic table, as we saw in that diagram at the beginning when we talked about homonuclears. So as we work left to right across the periodic table, the energies of each type of atomic orbital gets lower. So what do my molecular orbital energy levels look like? Oh, jeepers. Well, let's see. Let's start with the pi, because that's easiest. There was only 2 sets of degenerate pi molecular orbitals. So we took the px on the carbon and the px on the oxygen, and we combined them, and we made something that was bonding, so it should be lower in energy than both, and something that was anti-bonding, so it should be higher in energy than both. And then we did the same with the 2py. And you should definitely recognize that those are degenerate sets and therefore have equal energy to each other. So that's going to be pi bonding, and that's going to be pi antibonding, or pi star. Then we took our 4 sigma symmetric atomic orbitals and combined them to make 4 sigma symmetric molecular orbitals. Well, the lowest energy one is going to be lower in energy than everything that came to make it, and it was bonding, so it goes down there. And the highest energy one goes higher in energy than everything which made it. So let's put it up here so we can still read it. And the 2 in the middle are a little trickier to think about where they should go. So what's a good trick for knowing where they should go? Well, CO has 10 valence electrons. What homonuclear diatomic has the same number of valence electrons? What homonuclear diatomic is isoelectronic with this? And the correct answer is diatomic nitrogen. N2 also has 10 valence electrons. In the N2 diagram, we had 1 sigma at the bottom, and then we had 2 sigma, and then we had pi, and then we had sigma again, and then we had pi star, and then we had sigma star. It is reasonable to conclude, and is in fact backed up by experimental evidence, that carbon monoxide, which is isoelectronic with nitrogen, will have its molecular orbitals in the same order. So basically, place the lowest energy one below everything that combined to make it, place the highest energy one above everything that combined to make it, and place the ones in the middle so that they're in the middle in relatively reasonable spots. And if you have an isoelectronic homonuclear diatomic, use that picture to guide your decision. So here we have sigma and sigma, and the bottom one was 1 sigma, the next one up is 2 sigma, the next one up is 3 sigma, the top one is 4 sigma. Of the pi's, the lowest energy one is 1 pi, the next one up is 2 pi, and this is the point at which I give up on drawing my tie lines. Everything's made from everything. And you can probably imagine that, yeah, we do give up on drawing tie lines pretty darn soon, because our pictures just get way too complicated if we were to try and draw them all in. Oh my goodness, look at all these crazy, crazy, crazy tie lines. The last thing we should do is fill in our electrons. So we have 4 valence electrons coming from carbon and 6 valence electrons coming from oxygen, giving us a total of 10 valence electrons. And you'll notice I haven't actually committed to whether I'm going to call my 2 sigma and 3 sigma bonding or anti-bonding or non-bonding based on my pictures on the previous page. It's probably reasonable to say that the 2 sigma might be anti-bonding, but we'll take a look at the pretty computer picture in a minute to talk a little bit more about that. So here is the pretty computer picture. Again, I should fill in my electrons. So we had 4 from carbon, we had 6 from oxygen, and that puts 10 here in the middle. And you can see that we have been provided with nice, beautiful sketches of what those MOs actually look like. We did a pretty good job of predicting the shapes of the pi and the pi star molecular orbitals. We've got that polarization. The 1 pi down here looks a bit bigger on the red dot or the oxygen. The 2 pi star up here looks a bit bigger on the black dot or the carbon. So that's looking pretty good. As you can see, the 1 sigma looks almost entirely like 2s on the oxygen that's kind of been stretched over to the carbon a little bit. So this is the result of minimal mixing. It's very slightly bonding, maybe. Our 2 sigma has that 1 node that I suggested we look for, cutting right down through there. Our 3 sigma has those 2 nodes, and our 4 sigma has the 3 nodes. Our 4 sigma is most definitely anti-bonding. We've got a node cutting right down through the middle of that CO space. When we look at the 2 sigma and the 3 sigma, again, it's a tough call because, yeah, there is 1 node in that 2 sigma, but is that actually going down in the space between the carbon and the oxygen, or is that actually going through the oxygen nucleus? Because if it's going through the oxygen nucleus, then this sucker is non-bonding. And similarly, we'll find that there's actually some experimental evidence that suggests that the 3 sigma is also non-bonding. And if you look at the shape of that MO, you can say, well, yeah, there's electron density right in that middle internuclear region, but that's not a big lobe. The big lobe is on the outside. And so at this point, we really can't make a call based on just looking at the pictures. At this point, we really need some experimental evidence to back us up and tell us whether those middle orbitals, the 2 sigma and the 3 sigma, whether they are in fact a bonding anti-bonding pair or whether they are actually both non-bonding. The other evidence that could be argued to suggest that the 3 sigma is non-bonding is the fact that it is almost exactly halfway in energy between the 2p on oxygen and the 2p on carbon. And that means that the average electron in that orbital would be, if we put 2 electrons there, it would be the same on average as having 1 electron in the 2p from carbon and 1 in the 2p from oxygen. But again, this is where